Okay, thank you very much, Isabella. Hello to everyone. What I'm going to try and do today is give a little bit of a summary of my own personal opinion of where we are with compressive sensing and what we should be expecting for 2026. I should give a disclaimer up front. This is not supposed to be completely exhaustive. It's not supposed to give any particular opinions of one technology over another. It's just really to talk about where things are going. And if I've missed anything out that you believe that should be included in this, please let me know. I'm more than happy to have a discussion on technologies that are not included here. All right, Isabel, next slide, please. Okay, so the first thing we should talk about is what exactly is compressive sensing and how does it work in the case of scanning electron microscopy, scanning transmission electron microscopy, and even for TEM. So we all sort of are familiar with the way an SEM or a STEM works, and that's what you have listed as A here as a raster scan, where everything goes kind of like a typewriter. You go up the top row, you get to the end, you flip back to one row down, and you go along and go in that way. And that's the traditional way that all scanning techniques have worked with this raster approach to scanning. Now, you could do a scan in a different way, and that would be to say that we could do randomly going from different points and take the scan in a different way. There are some technological things that go into that, which is you have to have stability of your scan. You have to be able to jump from one place to another, and it has to be stable when you get there. But you could do a random scan. You could then go into a subsampled random scan, which says that actually you don't have to fill in all the pixels. You just hit some random pixels in particular locations, and that would be doing a sparse sampled scan. And then you can have one which would optimize the use of the equipment that allow you to get a sort of pseudo random approach. And this is the one that Sensei uses, which is called the line hop or subsampled line hop scan, which is basically say it's like the typewriter scan, but it has a random walk associated with it. And from doing that, we can get a random subsampled way of forming an image. And this is the first part of doing compressive sensing, which is to say that we can get things to be a little bit quicker if we don't acquire all of the pixels. So if we only use 10% of the pixels, we can be 10 times faster in acquiring the image. The trick, of course, is then you have to reconstruct that image to get yourself the fully sampled image. And that's really where the compressive sensing part of it comes in, which is the algorithms that are used to reconstruct your full image. And what you'd ideally like to do is to find out how few pixels you can take and still be able to fully reconstruct an image. So that's no loss in the image. And that's essentially the process for electron microscopy, reducing the pixels down to a much lower level, acquiring with lower dose because you've got fewer pixels, faster acquisition, get less data, and then reconstructing the full image. Next slide, please. So in the last year, there have been some notable applications, and these are people that have talked with Sensei about doing compressed sensing. And they're all really going for all of the three things that I talked about in the previous slide. In the case of Radboud, we're talking about going 4 times faster, a quarter the dose, getting volume EM results, getting in situ TEM microscopy data to come out. CNR, IMM are looking at doing 4D STEM data with 10% of the data acquisition and still getting all the information to come through in that process. At King's, again, they're looking at volume imaging, trying to get information, quarter the pixels, 4.5, 5 times the speed in terms of the acquisition, looking at very large areas, doing a lot of data analysis, but with much less data and getting the same resolution. And in that case, when we've got dealing with fewer pixels, one of the things I didn't mention in the first slide is if you have a sample that charges, and this is particularly important for all cryo applications, then by going to the sparse sampling, you're putting fewer electrons into your sample, so you have fewer charging effects, and so any of the degradation that you see in normal imaging gets reduced. And those things are coming through with the King's results. And then most recently, NYSBC looking at both the 4D STEM and also the volume imaging side of things to really improve the quality of the data that comes out on the structural biology side. Next slide, please. So I think the summary that I put together for 2025 was really that it was the year of the hardware upgrade. So there are lots and lots of companies out there that are now really supporting sparse sampling on the instrumentation level. And this is the first part of getting compressive sensing that I talked about in the first slide. First part is you have to be able to get a sparse sampled image to come out. Second part is reconstructing it. So now, whether it's upgraded scan generators, so all of the major manufacturers of STEM and SEM are upgrading their scan systems. So those scan systems now allow you to get some form of sparse sampling, whether it's a line hop or a random subsampling or using a beam blanking method, because you can also get random subsampling by doing a regular scan, but blanking the beam at random pixels to get rid of the intensity that goes into it. There are many ways that you can do it. There are many third-party scan boxes that you can get that can upgrade scanning systems on old microscopes. These are again giving you the increased precision that allows you to generate the random scan, and that allows you to do the compressed sensing. So then you can go through and use applications, and those applications can be in situ microscopy, they can be high resolution microscopy, volume EM, all of those things. And if you look at the list here, you're pretty much looking at covering most of the hardware that you can use on advanced electron microscopy and have the capability of being able to acquire a random scan or a subsample scan in that process. So on every microscope nowadays, it's essentially a reality that you can do sparse sampling, or you can do sparse sampling with a very simple upgrade to the system. Next slide, please. So what we do with Sensei, and as I'll talk about a little bit more as we go through, the Sensei side of the process is really the reconstruction bit. Once you've got your sparse sampled image, how do you do the reconstruction that allows you to get back to the full sampling? So if we put the sparse sampling of the hardware together with the reconstruction of the software, what are the things that are very close to happening or either happening right now? The first thing is we can start thinking about hardware-aware sparse sampling. What this means is essentially, what are the signals that we're getting? How can you use the signals together to reconstruct a better image that has information, let's say, from an EDS spectrum, an EEL spectrum, a secondary electron image, a backscattered image, a 4D STEM image, an EBSD image, and actually bring them together to make one image that contains most of the information that you can get from all of those techniques. Because if we're only taking 10% of the pixels, we can take information from all of those simultaneous detectors and combine them together. What we can also do with that is actually make the scan smart. So to start with, our first scan would be a random sparse sampling, but there's no reason why the second scan has to be random. What that can do is adapt to the image that we have generated and then take the second image that fills in the missing information and gets you the best image that's the subject from two sparse sampled images together. So you're still below the sampling of a full image, but you've now adapted to the bits of information that are missing for your image. You still get the benefit of the speed, still get the benefit of the lower dose, still get the benefit of less data, but now you're adapting to the sample that you're beginning to acquire. Second thing that's going to come onto mainstream is really using 4D STEM. 4D STEM is actually one of the easier methods to do in the hardware of doing the scan, because the dwell time is actually longer than you would get if you were just doing a regular 2D imaging. So that means the stability of the scan is less of an issue, and it's easier to have the dwell times and move the randomness about. So if you can already do that, there's no real reason why you shouldn't just do 4D STEM in a sparse sampled approach. Obviously, you have to reconstruct it, which is a key thing that I'll talk about as we go through. But essentially, there's almost no limitations coming in terms of the ability to do subsampled 4D STEM. And so if you can do it on everything, then why wouldn't you do it? Because you get less data, easier to do the reconstructions. And as I'll show as we go through, if you use the Sensei software, you can get a live reconstruction of the 4D STEM while you're on the microscope. So that allows you to optimize the process. EDS, EELs, those are things that are already used in many experiments for material science. And so there's no reason why those can't be implemented within the sparse sampling. Those are examples that are already underway, and I'll show an example as we go through towards the end of this presentation. But essentially, when you get into hyperspectral imaging, you can think of having both 4D STEM, EELs, EDS, all at the same time, all combined to give you those images. The other thing is, as I talked about in pulling all of these together in a hyperspectral data cube, what you can use for the reconstruction, because if you're using a scan probe to form the image, all of the signals from all of the detectors are related to the position of the probe. That means you can use an image of something that has a high amount of scattering to reconstruct something that has a low amount of scattering. So for example, in a stem, you could use a bright field stem signal to help you reconstruct a very low signal from EDS and EELs to improve your EDS and EELs map. If you're doing an SEM type experiment, you could use a secondary electron image to reconstruct your EDS or your EBSD map if you're trying to do something over a large area very quickly. So those interactions that are also related through to physical models of what the sample will be would allow you to get to the point of really getting high resolution images from a lot of different analytical techniques. And then as we're going through that process, that would allow us to very easily establish error metrics for the quantification of the reconstruction. And that means that every image that you get out in this way, you will be able to have an estimate of how accurate the algorithm believes that that image is going to be based on the information that's put into it. Next slide, please. So what we anticipate using Sensei for the reconstruction, again, what we're saying here is that the hardware, there are many places you can go with this, and it's really your hardware of preference, whether you already have it or you're working on that in that direction. What Sensei is doing is then looking at the reconstruction. So there's a vast array of new experiments on the horizon. You can do in situ experiments, and some of the developments that we've got with DEN solutions is looking at using in situ sparse sampling, ultra-fast electron microscopy, and then hyperspectral I've already mentioned. From the TEM and STEM side, we can also look at going into an SEM side, correlated light and electron microscopy, because the reconstruction approaches using the dictionaries we use for the compressive sensing will also work for optical systems, also works for different resolution between images. And so that allows us to transfer images between both the optical and the electron microscopy side of it. I'll talk a little bit more about this in my last slide, but potentially we can use 4D STEM to do single particle analysis. And if we combine the single particle analysis in the STEM at the highest resolution, so you're basically doing cryo-electron tomography, then you can also link that through to what you're going to do in the volume SEM and cover multiple length scales in that approach. For material science, the experiments that we do, obviously there's a lot of work that goes into getting a single image to come out, whether it's worrying about beam damage, whether it's worrying about complex systems, looking at interface and defects. In a lot of cases, the amount of time to get an image is very difficult, particularly if you're going to try and use 4D STEM. And the reason it's a lot of difficulty or time consuming is because you don't have a live reconstruction of your 4D STEM data or your map that you're going through, and you have to do that post-processing. So you never know on any microscope whether you've actually got the information you need, and that requires us to do multiple experiments to get it to work. Because we can do a live reconstruction of these images and the spectroscopy that we're doing, we can actually have a very rapid throughput. You get much quicker experiments, and that's good for R&D, and it's also good for metrology. And then as we go to adaptive sampling, we'll move towards an automated microscopy approach. Next slide, please. So if you can run the movie. So here is just an example of the live reconstruction. These are gold nanoparticles. This is an experiment done with a QD scanning system and Merlin camera on a microscope at the RFI. On the left-hand side, there are the 4D STEM patterns. In the middle, you can see the subsampled acquisition. At the bottom is the reconstruction matrix, so a dictionary that's used to form the image. And you can see that we can get a live reconstruction of a dark field image using the 4D STEM pattern here. The important about the compressive sensing compared to other artificial intelligence techniques is you can see that we can change focus, we can change magnification, we can change position. We don't have to do any learning approach to this. We don't need any training data. We get a live image. You can also see that the image reconstructs the data that is available. At the bottom of the image, on the bottom left corner of this gold nanoparticle, you can see there isn't an atomic resolution image. And that's because we don't have any resolution in our subsampled image to be able to reconstruct the atomic structure in that location. And this is a key factor of compressive sensing, no hallucinations. If the image isn't there or the information isn't there in the sparse sample data, you will not get the reconstruction going forward. So effectively, what it means is we have a live way of reconstructing our data, working out where the resolution is going to come from, and not having to worry about training data or getting any hallucinations in the results that we're doing. And that really speeds up the experiments moving forward. Next slide, please. So the other part of that is that in that reconstruction there, that was designed to show the fastest reconstruction that we can get so you can do live imaging. But once we've got that sparse sample data, that's enough. We can transfer it around, we can use it. And after we've come off the microscope, knowing that we're in pretty good shape in terms of the focus and the magnification and what we're trying to get out of it, we can then use our dictionaries to improve the resolution of our data. This is like a denoising or a deblurring effect that we can go forward. And here is just one example, again, of those gold nanoparticles. You can see on the left-hand side, the 25% signal reconstruction is pretty high resolution. But if we go ahead and use our dictionary to look at each of the individual layers in the image, we can vastly improve the spatial resolution of our data post-acquisition. Now, the important bit about this is that if you look at denoising, and everyone's trying to do denoising in some shape or form, a lot of it requires a lot of training data. A lot of it requires a very high performance computer to be able to get it to work in any kind of time domain. Here we can do it using our dictionaries that would come out of the compressive sensing, and that means that it can be done on the same laptop that's used to acquire the data and go through that process. So no extra compute power, we can denoise and we can deblur. And the deblurring is also important because always when you try and denoise, the way denoising works is it blurs out the image because you get rid of some of the high spatial resolution data. By denoising and deblurring together, you preserve that information. And that's very important for reconstruction of images. Next slide, please. So another example is with EDS datasets, and we can basically go ahead and compare the compressed sensing way of doing it. We can decrease the acquisition time, we can decrease the subsampling. And if you look at a quantification of, in the case of this alloy where you have two phases, you get essentially the same compositional result, but with 25% of, with 4% of the data, which means the whole thing is 25 times faster to get the result to come out. And this is just a raw reconstruction of in-painting each EDS spectrum, even in the places where we have missing data. It's not going into putting a physics-informed model into it, which will speed it up even further. It's not going into using an SEI data to actually help you improve the reconstruction. We're already to the point of 20 times faster for our EDS maps. And the next slide, please. And then the final bit, which I think will help to maybe spur some of the questions, is that what we want to be able to do is to use 4D STEM to do single particle analysis. And there's this paper that I've shown on the left-hand side here from a few years ago now, using tychography for cryo-EM specimens to show that you can get, under the same kinds of doses, the images. But in the end, we want to get into a tomographic reconstruction of the particle with the resolution that allows us to understand what the function is going to be. So what we've started to do with the Sensei approach is to essentially go through and say, let's just look at the denoising, deblurring effects on cryo-EM data and see what the reconstruction comes out when we run it through CryoSpark as a reconstruction. Now, we know that we can get the 4D STEM data. We want to know that we can run it through CryoSpark, which we can show here that we can. And then the next step of this process coming in 2026 will be to use the 4D STEM data to run that through a reconstruction with CryoSpark. And those things are essentially in the works as we go. And I think that's my last slide. And so hopefully those slides would help you show what we're up to, where compressive sensing is, and help to spur some questions, which I'm happy to try and answer any questions that anyone might have from now on.
All right. As you all are typing your questions into the question box, we do have one more question for the audience, and that is, how would you like for us to follow up? Are you interested in learning more about the Sensei solution? Maybe you're curious about your specific microscope and how that configuration might look. If you'd like to speak with an application scientist, we're more than happy to put you in touch with them. Obviously, if you'd like a demo, we can schedule that as well. And if you'd like a quote, just to know how much this might cost to implement in your lab, we're more than happy to provide that as well. Okay, and as people continue answering that poll question, I think we can get started with our list of questions here. So, Gleb, would you like to unmute and ask your question out loud, or would you like me to read it out loud? Let's see. Okay. Let's just get started. I'll read the questions out. We've got quite a few coming in. Okay. Do the dictionary reconstructed images show any artifacts? If yes, is it stable?
So one of the great parts of the dictionary learning and the approach to it is that there is automatically an error metric that comes into it in terms of how accurately the number of dictionary elements are used and how many times they are used to form the reconstruction. So typically what happens if you end up with an area of an image which cannot be reconstructed, you end up with a blank space. So it's like the movie I was showing of the gold particle. In the higher resolution reconstruction of that, you can see that basically the orientation of the gold nanoparticle means that essentially that's a very small lattice spacing in that location. And under that compressed sensing acquisition, there wasn't enough information for the dictionary to be able to reconstruct atomic resolution. When we go up in magnification, we get the ability to resolve it, and the dictionary works. When we go down in magnification, there isn't enough resolution to see it, and you don't get any information. So essentially, what happens at every location of the image, you get a list of which of the dictionary elements are applied to reconstruct that patch of the image, how much they were used, and what the error metric is compared to the image and the previous reconstruction that goes into it. So essentially, the artifacts that come into the system are there isn't enough information to reconstruct on the resolution you want, and so you get no information in there or a blank part of the image. And so that is actually very stable. Now, that being said, obviously, if you think about you do a thought experiment on compressed sensing, we know that this works very well down to about 10% of the data. So if we go down to 10%, we can do it without any problem. If you went down to 1 pixel, clearly you can't reconstruct the whole image. So then the question is it 2 pixels, 3 pixels, 4 pixels, 5 pixels? So we know from testing on multiple data types, multiple image types, not just electron microscopy image, satellite images, pictures of people, that effectively at 10%, we can almost guarantee to reconstruct with no artifacts and no missing data, fully lossless reconstructions. When you go down to 1%, it gets a little bit harder to do, and you try to bring in, if you're doing microscopy, it would be physics-informed reconstructions that go into that, or images from a different type of a contrast. So a bright field image and a dark field image, or a bright field and EDS that go into that, and that improves that. But you get much below 1%, 0.1%, and then you're just simply not going to get the resolution, and that's the artifact that you get, and it's very stable. If you don't have enough sampling, then you're not going to get the resolution that you want in the image to get the results you're looking for. And that's the artifact that you get, which isn't really an artifact, and it's actually pretty stable that, you know, if you're not resolving the information, it doesn't get transferred into your reconstruction.
Okay, thank you, Nigel. Let's see. What's our next question here? Can Sensei work for EBSD type patterns?
Yes, absolutely. And we actually have a couple of papers that have been published on this. Essentially, in terms of the interaction, it works just as well. I mean, essentially, an EBSD pattern is almost like a 4D stem pattern for an SEM. So effectively, the way that works, we can in-paint that data. We can do it in multiple dimensions. So you can in-paint missing EBSD patterns. You can convert the EBSD pattern into a subsampled image, and you can in-paint the subsampled image. Everyone has a preference in the way that they deal with these multi-dimensional data sets that come out of this, but it works very well for EBSD. And if someone sends me an email, or whoever asked the question sends an email or contacts Nanoscience, we can send you the papers on it working for EBSD. If you search Google under my name for EBSD, it should come up with the papers pretty quickly.
Great. Let's see what we have next. So this person has a three-part question. First part is about the forward model. Second part is a question about sampling. And the third part is a question about uncertainty. So we'll start with the first question, which is, what is the measurement model and which assumptions dominate the reconstruction quality?
Okay. All right. So I'm trying to translate that into so essentially we don't put a model into the reconstruction. Now the sampling map that we use is essentially determined to be random. Now random is in the eye of the beholder to some extent in that process, but mathematically, as long as you don't have a uniform spacing of your pixels and a uniform set of directions, you can generate a random map. And that's the one I was showing in terms of this random walk. What that then is doing is learning from the image, informing these dictionary elements. And actually that one would have worked if you run that movie again.
Sure.
So if you look at the dictionary at the bottom, when it starts, you can see the dictionary is changing to fit to the sparse sampled image. And if you like, those pixels that we are sampling are our ground truth. So what the dictionary elements are doing are being refined so that the image fits the pixels we have of our ground truth in these patches, and then fits into the missing information to form that reconstruction. And that's the process going forward. And as I said, there is an error metric there in terms of how well they fit, how many dictionary elements you need to get it to work. And this is very similar to what happens in JPEG compression. So in JPEG compression, you can over compress the number of patches you use to form your image, and then you lose spatial resolution. And we all know that happens when we try and download an image from a website and it's been compressed. And when you blow it up on your screen, it all looks pixelated that comes into that. What we're doing is trying to find the balance between not losing any of that spatial resolution and forming a high quality image using our dictionary reconstruction to go through that process. And there are all kinds of metrics that come in with that process. I'm not doing a particularly good job of discussing the mathematics at this point because we were trying to be kind of general. But again, we've got quite a few papers out going through the mathematics of this process. And again, if you're interested and you want more information on that, happy to send you the papers, happy to do this offline with more of the mathematical details. But essentially, the way that you fit the dictionary to the image, you know how many dictionary elements need to make a good fit, and you also have an error metric of how well that fits. Of course, once we reconstruct the image, then you have the resolution in the image. So if you look at the one that's on the screen, that's a gold nanoparticle. We know the lattice spacing of gold, so we can take a Fourier transform of the image and see how well that corresponds to the known gold spacings that are out there. So once you're back to the full image, you can then use your image and the information in the image to actually evaluate how well it has reconstructed the image that you're trying to look for.
Very good. So this second question, I think they're asking for your opinion, I'm assuming, but they want to know what you think, which sampling pattern you think is theoretically or empirically the best.
All right. So it's a much more nuanced answer than that in the process, and some of it depends on the speed, right? So in the way that compressive sensing was originally designed, it would have a completely random set of pixels, and if you were sampling something, you would go from the top left to the bottom right to up and down and around in all kinds of different ways. Now, the problem with that for an electron microscope is practically you have to accurately move the beam to each of those locations. It has to stop in that location, and then you have to move it to another one. Now, if you're trying to do a very fast image, like if in STEM you're trying to do a bright field image or a dark field image, and you're talking about microseconds, very few microseconds of dwell time, or an SEI image in an SEM, then if you try and do that, then basically the drift in the beam when you try and move direction, the hysteresis in the scan coils means that you very easily lose the place that you're at. So that pure random pattern begins to go away in terms of its optimal way of doing it. So then you go to what we try and use, which is to say that, for 70 years, an SEM and a STEM has been optimized to go from the left-hand side to the right-hand side, fly back to the beginning, and then go again. And when it flies back to the beginning, it usually stabilizes at that location for a while. And that's why if you ever turn the magnification down with the STEM, you usually see a damaged track on the left-hand side. Now, some of the STEM manufacturers cut out that left-hand bit so you can't see it when you're running at high resolution, but you turn the magnification down, you see that out. So if you go with our random walk approach, what you're doing is sort of randomly scanning in that direction, but you're following in the direction that the scan has been designed to do. And that means that by only stepping one point up or down as a function of going left to right, you minimize the hysteresis in the scan. Now that works very well for the very fastest image, but if you look at the one that's on the screen, you can see that that's not a random walk pattern for the 4D STEM. And the reason for that is because when you stop to acquire your 4D STEM pattern, we have to stop for longer to get enough signal. Even with a very good detector, you're talking about 50 microseconds instead of 5 microseconds. At that point, it will stabilize, and then you can do a more random scan to go through that process. And that works well for the conditions where you have a longer dwell time where you're trying to go through that process. So an EELS map or an EDS map or a 4D STEM map, you can go back to this more randomized approach to going through the system. And that helps you to distribute the dose, which means it reduces the effect of the damage on the sample, and it allows you to get that information in a very accurate way and transfer. So it really is dependent upon the experiment you're trying to perform. The damage that occurs in the sample and the stability of the microscope and the speed that you're trying to acquire the image.
Okay, thank you, Nigel. I think we'll revisit this third part of the question. There's another question here that I like. How have you done quantitative analysis on minimizing charging effect through sparse scanning, specifically in volume EM?
Right. So we did some analysis of this. Now the way that a lot of it's easy to do is when you do the volume EM, and this is work that was done at King's by Roland Fleck. Essentially, we see higher resolution in our images because the charging effects. So the streaking of the charging, we can resolve the features in the image a lot clearer because we've got less charges going into the system. Now, we haven't specifically tried to do it with different charging or beam levels to go through that, because essentially when you go to the sparse sampling, you're not changing the resolution of the microscope, you're not changing the magnification that you're working at. The only thing you're really changing is the dose and the dose rate that you're putting into the sample. So it's pretty easy to identify that as a charging effect that goes into it. So we don't actually even have to look at the physics or the math of the reconstruction process. We can actually look at the images that have come out and see that we get higher resolution in the images that we're getting, so that our 3D reconstructions that come out of our volume EM have higher resolution. It's things like membranes that are under the charging effect look like they have a single wall that's very broad, and when we go with the sparse sampling, we can see a double-walled membrane and go through that process. So there's lots of ways that we can understand the image, and again, it is really important to sort of conceptualize that once we've created our fully sampled image, you can do all the resolution checks you would do on a normal fully sampled image. You can take a Fourier transform, you can go through that process. In terms of looking at the accuracy of our reconstructions, though, one of the things that we've tested on many cases is basically just taking a fully sampled image and artificially cutting out the pixels and doing a reconstruction, because then you have a ground truth and you go through it. It also works where you take a fully sampled image and then you go ahead and you take a subsampled image on the microscope, and again, you have a ground truth and you can compare to those. And that's why we know that 10% of the pixels, as long as we stay at around 10% of the pixels, we're going to get a very good reconstruction that comes out that's very accurate. Now, the problem with this, of course, is that if you have a sample like that doesn't damage, doesn't charge, doesn't have a problem with the acquisition, you don't have to go any faster on the image, then why on earth would you use compressed sensing? Compressed sensing works for images that you can't acquire any other way. And of course, if you can't acquire the images any other way, you don't have a ground truth to compare to. And so that's where we very conservatively say that we know in this range. So we've done reconstructions down to 1% and 0.1% of the data in specific cases. But we don't say that, yes, if you use this for your volume EM, you'll be able to take 0.1% of the data. What we do is we say that on everything that we've tried, everything we've tested, 10% works very well, and you're guaranteed to get a good error-free reconstruction on all the images that we've tried when you have a ground truth. Now, it's fully clear that, okay, that's not the same as having a ground truth for some of these more sensitive samples. But if you could get a ground truth, then you wouldn't need to use compressive sensing. So that's the bit you have to deal with.
Okay, thank you, Nigel. The next question is, can compressed sensing offer any benefits to images already collected using standard scan patterns?
Yeah, so it turns out the example that I showed, which is actually the slide after this one, Isabel, I don't know if you want to click to that one, is that essentially because you've got this dictionary that you can go through, we can actually use that to denoise samples. In-painting by itself actually does a denoising, without the in-painting bit, denoises the images that you've got. By taking the dictionary elements and using them on different parts of the images with different weightings and going through that process, we can actually denoise and deblur the images as well. And because it's based on a dictionary rather than on a trained set of data, you don't need any extra computing power to be able to do this. And you can run these denoising, deblurring algorithms using this process, using pretty basic computing to be able to get that to work. Because essentially it's all about the dictionary elements that you use. And here is just the example that showed. We could all see that fast live reconstruction looked a little bit blurry when you went through it. And that's because it's using the lowest spatial resolution part of the dictionary elements with the highest contrast to reconstruct the image live so that we can get rapid feedback. But once we've got that, we have the dictionary elements, we have the sparse sampling that we know that we can reconstruct, and then after we've acquired the image, we can go back and reevaluate that and say, right, rather than trying to get the fastest result, how about getting the highest spatial resolution result, the one that converges to the most accurate way of doing it. And the important thing on this image here is that you can see that the big gold nanoparticles are much better resolved in terms of the atomic structure. You can even resolve those blurry bits that didn't come through in the compressive sensing live reconstruction. But also, very importantly, you can see all of the individual atoms that are sitting in between these two nanoparticles. And you can even see that some of them are moving around because they've come across as being slightly distorted in the way that they're going through. So we can resolve all of these images having got to that best condition. We know from the live image that we're at the optimal focus. And then afterwards, we can go ahead and reconstruct to get the optimal image. The live image lets us get the optimum conditions. The post-acquisition doesn't need training data because we know that our acquisition is already at the optimal point. We can go ahead and reconstruct using our dictionary elements. And that can apply to any image. And we could go through and apply it to any either image that's acquired. Obviously, the benefit is to be able to make the acquisition optimal, and fixing an image that's already been acquired. In a lot of cases, all you do is find out that the image wasn't acquired in the best way that you can do it, and you can't overcome distortions caused by defocus, astigmatism, just lack of signal. There's a limit to what you can overcome, but it still works, and it still does provide, in many cases, an improvement in the signal quality that you can get.
Thank you, Nigel. Sounds like there's so many different ways that compressed sensing can benefit different microscopy users, both during acquisition and after. So that's very exciting. Let's see what our next question is. So this person has a question about the Sensei installation at New York Structural Biology Center. I believe this was fairly recent, so I'm not sure that we have too much to share in terms of the data that they've been acquiring so far. But they're curious if you have any more details you can share about incorporating Sensei into their workflow for cryo-EM.
Well, yeah, I think it's up to them to talk about their system more than anything. All we can say is that the way that Sensei is installed is that essentially it takes about 2-3 hours a morning to install that system. We've installed it on a couple of their microscopes, and obviously they want to use it to get higher speed, less damage, lower dose interactions in the process they're doing. I prefer not to talk about it's their science. They want to talk about that. But in terms of the installation, as I was trying to say, with 2025 being the year of hardware development, essentially we can install the software on any microscope into that system, whether it plugs in through an external scan generator or just plugs into the external port that is used by EDS manufacturers and to take over the scan. It's a very straightforward installation. Once it's installed, it doesn't change everything else. You can turn it on or turn it off. Doesn't really matter. It's not a hardware change to the system that's causing all of the other methods to not work. It's not when you install it, you have to use that. It's just a system like if you turn on your EDS, you turn it on, you can use the sparse sampling and go through that process. And it doesn't take more than half a day to do that installation, and it doesn't take more than a day or so to train people on how to use it. It's like any software process. It's very similar to running a microscope. You just run it through the sparse sampling acquisition, and that installation took place in December at NYSBC. So they've had it for about a month, and half of that month was the Christmas holiday. So.
Yes, I'm sure we'll have more to share in the future, but we'll keep you updated, and you can keep an eye on their publications as well. The next question reads, very nice presentation. Thank you, Nigel. Do you think compressed sensing can also be applied to diffraction data?
So diffraction data is already very, very sparse. And so the process is a little bit, so in like TEM diffraction, it's all very, very, very sparse data. In 4D STEM, of course, it's not a sparse data set. 4D STEM is essentially a diffraction pattern that's an image. And there we already know that we can in-paint missing patterns and we can go through that process. So that's not too much of a problem to go through. In terms of a pure, like a TM selected area diffraction pattern, by definition, that's already sparse. It's just the Fourier components. And it doesn't really give us any extra information to try and in-paint that information. But 4D STEM data, which is diffraction data, absolutely. Nanobeam 4D STEM data, that we can do things with in-painting and fill in missing information and deal with lower signals. That's actually very, very useful to do, but selected area diffraction, no.
Okay. We have time for a few more questions. I do want to let everyone know if you have additional questions, please do drop them in the question box, but we still have quite a queue, so let's continue working through it. This one I think is maybe not specific to Sensei, but more a conversation about automated models in general. Can drift be learned via a machine learning model? A model that, for example, returns a correction to the control signal to move to the intended coordinate?
So I think, yeah, so I will answer a different bit of that question, which is that essentially the compressed sensing is not a machine learning model per se in terms of what goes into that. It's a reconstruction model. But absolutely, we can use the compressed data to do a drift correction in that process. By definition, if you have enough sampling to reconstruct a full image, it means that anything you could do to that full image, you can do on the compressed data set, right? The mathematical methods can be applied sequentially, or they can be applied at the same time. So what that means is that we can, because we can do drift correction from the acquisition of images, with the compressed sensing data set that we have, we can do a drift correction on that in that process. That's not really using a machine learning per se way of doing it. It's just using that to correct the differences between the images. The advantage of doing it in a compressed sensing way is that because we're acquiring fewer pixels, we're acquiring much faster images, which means you're going to get much faster feedback in terms of the correction that you have in the drift. So absolutely, we can do that with the compressed sensing. It's not something that we have particularly done so far. And the reason for that is that all of the microscopes that we've applied this to, the speed of the imaging is such that we can actually get a full image before we have to do it. You can see it on these gold nanoparticle images. There is some drift in there, but some of that's caused because we're changing the magnification sequentially, and that will affect the process that goes on. But absolutely, drift correction is part of our development process, and we expect to have something on that coming up later in the year, maybe into next year.
Okay, thank you, Nigel. So this person has a question about pure TEM. You mentioned compressed sensing for TEM. Can you elaborate on how that works?
Yeah, so if you think about, let's do it. So you can think about a STEM image of acquiring the pixels sequentially, and we're missing out pixels. But let's say you take a TEM image, which acquires all the pixels simultaneously, but you turn the dose down to the point where there isn't scattering into all of the pixels. You've effectively subsampled the TEM image in that process. And so that means that a lot of the in-painting will work in the same way on a very low dose TEM image. And you can in-paint the missing information using exactly the same algorithm for low dose. So I mentioned in the presentation the idea of using it for ultra-fast TEM. The biggest problem with doing ultra-fast TEM is you don't have enough electrons to get high resolution. But if you use an in-painting mechanism to do that for the very low doses that are going into there, you can improve the signal to noise in your acquired images, and then that will give you a higher resolution image for the same dose that you get. Now, the gain is not as much as for the STEM, because in the STEM you're trying to do a sequential acquisition, but it does improve the images that you get and gives you a better signal to noise. Effectively, you can think about it as just doing a denoising effect on your TEM image. And so you're using the in-painting to denoise your TEM image under extremely low dose conditions. But the reason it works is because under extremely low dose conditions, only 20-30% of your pixels in your TEM camera has got any scattering in it. And so it's a subsampled image, and so it will work in the same way.
Okay, thank you, Nigel. Let's go back to this question. This one's about uncertainty. How do you quantify reconstruction uncertainty, not just the image quality?
Yeah, so as I said, the way that we have done this in the past is to use a ground image of a sample that doesn't damage, doesn't drift, doesn't do it, and just take a ground truth fully sampled and a reconstructed image. And then you can use things like PSNR to go through an SSI to basically measure the difference between the reconstruction of the image and the ground truth image that you've got. And that gives us an uncertainty in the image that we get out. And that's where I say that if we stay 10% and above in terms of the subsampling, we know from all of our ground truth experiments that we have done that essentially we're going to have a level of uncertainty in the image that means that a human cannot really see the difference between the reconstructed image and the ground truth image. And now, mathematically, the PSNR still has several levels to go in terms of doing that. But if you actually, what we did in tests where we actually asked users to say which is the best image, in some cases they told us the one that had the poorer PSNR from the reconstruction was actually a better image to look at than the one that had a higher accuracy from the reconstruction and a better quality that goes through it. So once you get in the 10% that I was talking about, the reconstruction is accurate enough that it becomes in the eye of the beholder at that point. So it's up to the person using the microscope or with the image to say which is the better image, because mathematically we can show that they are better, accurate, more accurate reconstructions to the ground truth. But to a person looking at it, they can't really see the difference between the process. And that's why we always use that 10% bit. We can go below that, but then it becomes a little bit more of a problem in terms of the accuracy. We already know what that accuracy is as well, and we can quantify that because, again, the easiest way to test it is something you have a ground truth you can measure it from. And so we know that if you then try to do an unknown experiment, you're going to have a certain accuracy or a certain error bar associated with that reconstruction, which means you should be able to deal with it accordingly in that process. But above 10%, we're pretty much sure that the reconstruction and every test that we've done will get us something where it's in the eye of the beholder. And if you have some data that you think will be different, more than happy to run it through our system and go that and give you the error metrics. We do that every time to people who inquire about using this. A lot of times they send us an image to say, what can you do with this? And we can go back and just basically quantify what that reconstruction is that comes out of it.
Very nice. Okay. We have a few more questions. I know we're sort of running out of time here. So if for whatever reason we don't get to all of these questions, I do want to emphasize we will follow up with you after the webinar. We're not just going to leave you high and dry. An application specialist will get back with you with a specific answer to your question. So can Sensei also work to visualize electric fields with low dose?
Yeah, so what if you can get an image contrast out of a microscope or an imaging system, then Sensei can help with that, right? So what it doesn't do is it doesn't change the contrast mechanism. It doesn't change any of the physics of the processes involved. All it does is say that we can get away with acquiring fewer points for that, or a lower dose from that. So it's more noise limited in the process, and it can help with that. It doesn't change the contrast in any way. We're not changing the physics. It doesn't change the process. So what it means is it's a way of helping with any signals where you have problems seeing things. So we've looked at, for example, skyrmions before in terms of getting information on that. We've been looking at fluxons in terms of the process that you see with that. When we go and do 3D volume imaging, those aren't really giving us information on atomic structures. They're giving us things that we don't really know the shape of a priori, and we can reconstruct it. And the reason we can reconstruct it is we're not changing the physics of the scattering process. That thing is a constant. And so that means that anything that has these problems in any image of any type is going to be a benefit if you can use the Sensei approach to basically improve the signal to noise or in-paint the missing information.
Okay, and one more question. How does Sensei benefit EELS experiments in terms of signal to background ratio?
Okay, so there are two things that, there's several things that we can do with that. So the first thing is that you can actually acquire the image in a subsampled way. So you have a detector. So an EELS signal is a one-dimensional signal. And so if you had a detector that was basically columns, so we can move the image across the spectrum and you end up with a compressed sensing spectrum. That means that the time resolution of our spectrum is about the frequency of which the detector or the spectrum moves across the detector. That means for any data cube where you're acquiring an EELS map, you're basically just moving the detector or the spectrum, and you get the resolution of the moving of it. What that means is that you bunch all the signals in together, you can then use a dictionary for the whole thing, and you can use the signal to noise of the whole signal rather than each of the individual spectra. So that is a benefit of getting EELS in that way. We then have the benefit of all the other signals that we're acquiring when we're doing our EELS map. So if you did an EELS map, you could also do an EDS map, you could also do a bright field, dark field, all of the ways that you would do those imaging simultaneously, and then use the information in those high resolution maps to help reconstruct your EELS image that you get out of the system. And then the third thing that we can do is obviously put a physics guided information into that, because we know what the EELS edges should look like. We can put the information into that. We can do DFT calculations and understand what the structures will do. We can make dictionaries from our simulations to help us interpret our acquired spectra. And all of that means that you can get much higher signal to noise information out from much lower acquisitions on your EELS side of it. And that's something that we will implement in Sensei in the coming year. And we expect to have it ready for M&M and for the IMC meeting coming up.